Venus, remember,
Well, it does, but humans can't land on it. See, there's a teensy problem with temperature. There's so much CO2 on Venus that the greenhouse effect makes the surface hotter than hell. Over 450 degrees Celsius, well above the melting point of lead.
Terraforming Venus sounds cool, but it's a total logistical nightmare. Imagine turning a scorching, toxic planet into a comfy Earth-like home. Sounds impossible, right? That's because it's crazy hard. Venus has crazy hot temperatures, a super thick atmosphere, and loads of other problems that make this idea a seriously tough challenge. In 1954, Paul Anderson wrote The Big Rain, planting the seed for terraforming, a concept later explored by Carl Sagan in 1961, who proposed transforming Venus. Despite earlier assumptions, Venus surprised scientists with its thick CO2 atmosphere, challenging notions of habitability. Now here's where the saga of Venusian transformation gets juicy. Sagan, in a classic move, proposed the injection of photosynthetic bacteria into Venus's atmosphere. Imagine a microscopic army turning carbon dioxide into something a bit more Earth-friendly. A noble idea, right? Well, in 1961, Venus was still keeping some atmospheric secrets up its sulfuric acid-laden sleeve. Fast forward again, this time to 1994, and Sagan, in his book, Pale Blue Dot, drops a bombshell. He admits his original terraforming proposal was a bit like trying to teach calculus to a kitten. Because, surprise, surprise, Venus's atmosphere was way denser than anyone had bargained for back in 1961. Change number 1, the atmosphere. Venus, with its thick coat of carbon dioxide, is like the cosmic embodiment of a sauna gone wrong. To make it hospitable, we need to find a way to thin out that heavy atmosphere. It's not as simple as opening a window. It's like trying to air out a sealed space capsule hurtling through the cosmos. Next up, change number 2, temperature control. Venus, notorious for its scorching surface temperatures that could melt lead, needs a cosmic cooldown. Imagine trying to chill a hot cup of coffee in the heart of a blazing supernova. Challenging to say the least. Change number 3, introducing a dash of Earth-like charm. We're talking about transforming Venus into a haven, with lakes, rivers, and maybe even a little beachside resort. But folks, it's not as easy as a cosmic holiday makeover. Venus is stingy with its resources, and turning it into a planetary paradise would require some serious cosmic elbow grease. Mark Bullock and David Grinspoon did some serious astrobiology math. They discovered that Venus's atmosphere, a hefty 92 bars of pressure, could have a love-hate relationship with surface minerals like calcium and magnesium oxides. Picture this: if we could convince these minerals to trap carbon dioxide in the form of carbonates, we might cool down the Venusian sauna. Now, the catch is that it's like trying to teach calculus to a comet. The equilibrium between the atmosphere and surface minerals is as stable as a spaceship doing the cha-cha. But if, and that's a colossal if, we could convert these minerals into carbonates, the atmosphere might chill out at a more manageable 43 bars. That's progress, right? But wait, there's more. Our space maestro, Alexander G. Smith, threw in an idea. Let's flip the cosmic script with lithosphere overturn. Basically, we'd need to expose more of Venus's crust to the atmosphere, giving us a shot at more extensive carbonate conversion. It's like redecorating the entire planet. A bit extreme, but hey, we're talking about Venus here. Now, if you're picturing bulldozers and interplanetary construction crews, you're not far off. We'd need to involve the entire surface crust down to a depth of over 1 kilometer. But here's the kicker. This isn't your average backyard makeover. We're talking about reshaping a planet, turning it into a cosmic masterpiece. Now imagine the scene. Venus, once a fiery inferno, now cooling down, a breeze whispering through its newly formed carbonated atmosphere. But this grand plan requires some serious cosmic engineering. We're talking about moving mountains, literally. Exposing the entire surface crust means we're in for a planetary-level construction project. Think of it as the ultimate celestial renovation. Now here's the kicker. The natural formation of carbonate rock is as slow as a comet's crawl. A Our recent research on Earth has cracked the code. With a dash of catalyst magic, like polystyrene microspheres, we can speed up the process from centuries to just 75 days. Now here's where it gets even more mind-blowing. What if we showered Venus with refined magnesium and calcium from off-world? Picture a cosmic bombardment of essential minerals. About 8 times 10 to the power of 20 kilograms of calcium or 5 times 10 to the power of 20 kilograms of magnesium. That's the cosmic recipe to convert all the carbon dioxide in the Venusian atmosphere. We're talking about mining and refining on a scale that makes your backyard garden look like child's play. We might even need to tap into the mineral riches of Mercury, our celestial neighbor. To put things in perspective, 8 times 10 to the power of 20 kilograms is a few times the mass of the asteroid 4 Vesta, a colossal space rock over 500 kilometers in diameter. Research projects in Iceland and Washington state have shown us that we can potentially suck large amounts of carbon dioxide out of Venus's atmosphere. How? High-pressure injection into porous basalt formations, where CO2 transforms into solid inert materials. Talk about a cosmic magic trick. 1 cubic meter of basalt has the potential to swallow up 47 kilograms of carbon dioxide. Now, to sequester all of the carbon dioxide on Venus, we'd need a volume of basalt equivalent to the entire crust, around 9.86 times 10 to the 9th power kilometers cubed. That's like giving Venus a new geological wardrobe down to a depth of about 21.4 kilometers. But there's more good news. Under optimal conditions, 1 cubic meter of basalt could slurp up a hefty 260 kilograms of carbon dioxide. With Venus boasting a crust about 70 kilometers thick, mostly made of volcanic basalt, we've got ourselves a potential cosmic carbon sink. And guess what? Research even suggests that under the sizzling temperatures and pressures in Venus's mantle, silicon dioxide can form stable carbonates. Now, let's talk about introducing hydrogen, a bold move straight out of the cosmic playbook. According to the cosmic maestro Birch, bombarding Venus with hydrogen and reacting it with carbon dioxide could produce elemental carbon, graphite, and water. Sounds like a recipe for a cosmic cocktail, doesn't it? To convert the entire Venusian atmosphere, we'd need a whopping 4 times 10 to the power of 19 kilograms of hydrogen. Where could we get such a cosmic stash? Gas giants or their moons might just be the hydrogen havens we need. Or what if we somehow tap into possible hydrogen reservoirs deep within Venus itself? Talk about a planetary treasure hunt. But wait, there's more to this cosmic mix. Iron aerosol in the atmosphere is essential for this reaction to work. Where could we get iron? Mercury, asteroids, or the moon could lend us a hand. And don't worry about losing hydrogen to the solar wind. It's a blip on the cosmic timescale. Now here's where it gets truly cosmic. Isaac Arthur, the futurist extraordinaire, suggests a mind-blowing idea. Picture this, a hydro cannon, created by starlifting and sterilizing processes, shooting ionized hydrogen from the sun. This cosmic water gun could thin Venus's dense atmosphere and create water by reacting with carbon dioxide. It's like a cosmic double whammy, reducing atmospheric pressure and introducing water to cover 80% of Venus's surface. But here's the cosmic catch. Directly lifting atmospheric gas into space is like trying to play interplanetary tug-of-war with Venus. It has this thing called escape velocity, making blasting its atmosphere away with asteroid impacts a bit impractical. In fact, scientists Pollock and Sagan crunched the numbers back in '94 and concluded that even a colossal impactor of 700 kilometers diameter striking Venus at lightning speed would only eject a fraction of the atmosphere. We're talking 1,000th of the total atmosphere, and to make a dent, we'd need an asteroid army. Imagine trying to vacuum a whole planet. Now, if we tried the bombardment route with a massive Kuiper belt object on a collision course, it might stir up Venus's insides enough to eject some matter. But this could result in a new moon for Venus or a debris shower headed back to the surface. It's like trying to hit a cosmic bullseye blindfolded. But let's not give up hope just yet. Maybe we can control the atmospheric thinning in a more elegant manner. Enter the challenge of Venus's sluggish rotation. It's a real headache for constructing space elevators. Picture this: geostationary orbits hanging out at a distance that's practically waving from another cosmic neighborhood. Mass drivers, useless against the thick atmosphere. Now cue the brainstorming session for workarounds. Imagine mass drivers hitching a ride on high-altitude balloons or towering balloon-supported structures, reaching above the atmospheric clutter. Think of space fountains and rotovators, cosmic inventions straight out of a sci-fi dream. But here's the cosmic curveball. Reduce the atmospheric density and you might unleash a cosmic weather drama. With less atmosphere to keep temperatures in check, the day side and night side of Venus could be playing an interplanetary tug-of-war of their own. Imagine intense weather showdowns at the Terminator, where the atmosphere undergoes rapid heating and cooling, a cosmic spectacle of epic proportions. And that's a wrap. So what do you think? Share your thoughts in the comments below. And don't forget to like and subscribe to our channel for more.